Welcome back to our video module on dynamics. In our previous video, we combined two concepts, mainly the center of a mass rotating about a pivot and rigid body rotation, to understand equations of motion that are valid for rigid body rotating about a pivot. Today, I'd like to take a look at the energy equations for this system. So let's scroll up. We'll keep the equations in gray, and we're going to review the equations for kinetic energy for each of these scenarios, scenario 1 and scenario 2. The kinetic energy for scenario 1 is simply 1/2 mv squared. Another way that we wrote that was 1/2 m omega r squared. Likewise, when we looked at the kinetic energy of a spinning disk, we understood that there was some energy due to the actual spinning of the disk. Kinetic energy was 1/2 I, and remember this I was about the center of mass, omega squared. Because we have both these types of motions, we'll have energy contributions due to both of them in scenario 3. So our scenario 3 kinetic energy is going to be 1/2 m omega r squared plus 1/2 I omega squared, the energy due to purely rotational motion. And if we wanted to be savvy about this, we'd factor out the 1/2 omega squared, and we'd be left with the polar moment at the center of the mass plus mr squared, which should look very familiar to you using the parallel axis theorem. We could also rewrite this as the kinetic energy is 1/2 I o omega squared. So we see the parallel axis theorem also in full use for our kinetic energy. Now, does this make sense? We can imagine in scenario 3 that, of course, we have the kinetic energy that we did before, where we had a point mass rotating about some pivot, rotating like this. But in addition, the merry-go-round also has some angular momentum due to the fact that it's spinning. So we expect that the total energy is higher in scenario 3. Another way to see it is that if we did some work in the form of some moment or some applied force on scenario 1 to get this thing to rotate, we could do the same force in scenario 3. Instead of the energy building only this component, mainly the energy required to spin some object, we're also going to see an additional amount of energy because that object has some angular momentum. So one can imagine if you applied some work in scenario 3 and the same amount of work in scenario 1, scenario 3 will have a much lower angular velocity because the work is building not only this aspect of kinetic energy, but also this aspect of kinetic energy. Whereas in scenario 1, you have the work only building one term, which means that omega is going to get a lot higher. So hopefully this brief intuitive look at kinetic energy and work in a rigid body rotating about a pivot gives you a more fundamental understanding of what's really going on there. In our next video, we'll take this analysis one step further by looking at pendulums that are not point masses. I look forward to seeing you then.